Hyun Lee's paper presents an in-depth examination of Wigner's friend's thought experiment, offering a new interpretation of quantum mechanics that redefines our understanding of Born's rule and the measurement process. This reinterpretation suggests that Born's rule should be seen not as a historical constraint, but as an intrinsic reflection of the coordination between states within entangled systems. This shift has led to the development of the Objective Relative State Formulation, ORSF, a new variant of pilot wave theory where microparticles possess definite states before observation. Quantum mechanics, the study of nature's smallest scales, frequently challenges our everyday understanding of reality. One of the most intriguing scenarios in this field is the Wigner's friend experiment, which examines the essence of observation and measurement. Wigner's friend scenario. In this thought experiment, imagine two friends named Alice and Bob. Alice is inside a lab experimenting on a quantum particle, while Bob is outside the lab observing both Alice and the particle. Quantum mechanics posits that before Alice measures the particle, it exists in a superposition capable of being in multiple states simultaneously, akin to a coin being both heads and tails until observed. When Alice measures the particle, she perceives a specific outcome, for example, heads. However, for Bob, who has not observed the lab's interior, the system, comprising Alice and the particle, remains in a superposition of all potential outcomes. This implies divergent realities. Alice observes a definitive result, while Bob considers all possibilities. Analysis of the original thought experiment. The Wigner's friend scenario involves two observers, W and F, with F measuring a microscopic system and W observing the composite system of F and the microscopic state. Traditionally, this leads to different realities experienced by the observers, an issue exacerbated in extended Wigner's friend scenarios, EWFS. These scenarios challenge fundamental assumptions such as the absoluteness of observed events, AOE, locality, L, and no superdeterminism, NSD. The paper contends that subjective interpretations, which allow for observer-dependent facts, fail to resolve inherent contradictions, necessitating a redefinition of Born's rule. Reinterpretation of Born's rule. Hyun Lee's paper redefines Born's rule, proposing it should only apply within entangled systems, reflecting internal coherence rather than the quantum state's history. Born's rule thus pertains to the projection of a subsystem within an entangled system and its coordination with the entire system. This reinterpretation implies that measurement outcomes are determined by the state of the entangled system as a whole, rather than by the pre-measurement state of the subsystem. New pilot wave theory, Objective Relative State Formulation, ORSF. The ORSF integrates the concepts of the universal wave function and relative state from Everett's many worlds interpretation, but aims for an objective interpretation where all observers' realities are harmonized. This approach treats the universal wave function as the pilot wave, guiding the system's evolution. The redefined Born's rule aids in consistently explaining Wigner's friend scenarios by considering the entire entangled system state rather than individual subsystems. Addressing contradiction with special relativity. The paper tackles potential conflicts with special relativity, particularly in space-like separated measurements. It proposes several resolutions, such as assuming a special temporal order for events or adopting a frame-dependent reality, ensuring that quantum correlations do not breach relativistic causality. However, the paper acknowledges that this remains an open issue. Significance and applications. This new interpretation significantly impacts our understanding of quantum measurements and reality's nature. It challenges the classical view, where measurement outcomes directly reflect the pre-measurement state, suggesting instead that outcomes are about the coherence of the entire entangled system. This perspective aligns with phenomena like the quantum Zeno effect, which demonstrates how measurements can alter a quantum system's state. The ORSF provides a framework for understanding quantum dynamics as the relative evolution between entangled states, offering new insights into wave function collapse and unitary evolution. Exploring the intricate nuances of quantum mechanics is aided by juxtaposing classical and quantum measurements. For instance, consider flipping a coin in a classical scenario. The coin lands either heads or tails upon observation, yielding a definite outcome. Conversely, a quantum particle behaves differently. Like a coin in a superposition, it exists in multiple states simultaneously, both heads and tails, until observed. This distinction underscores the fundamental difference between classical determinism and quantum superposition. Born's rule traditionally helps calculate the probabilities of different outcomes in quantum mechanics based on the particle's history. However, Qian Li's paper proposes a revolutionary interpretation, suggesting that Born's rule should reflect the relationship between the components of an entangled system, moving from a focus on the particle's past to understanding the dynamic interplay within the system. The objective relative state formulation, ORSF, advances this idea further. Imagine the universal wave function as a choreographer coordinating a dance, ensuring all dancers move coherently. In classical mechanics, this coordination guarantees a harmonious performance. Similarly, ORSF posits that particles have definite states before observation, but these states are coordinated within the entire entangled system, akin to dancers knowing their steps relative to each other. Applying ORSF to the Wigner's friend scenario, consistency of observations becomes crucial. Traditionally, when Alice measures a quantum particle, the wave function collapses, resulting in a specific outcome. Meanwhile, Bob, who has not observed the measurement, still perceives the particle in a superposition. Under ORSF, both Alice's and Bob's observations are harmonized by the universal wave function, integrating them into a consistent, larger reality. To illustrate this with another example, consider measuring the temperature of a cup of coffee. Classically, measuring the temperature yields a specific reading, say 70 degrees C. In the quantum realm, measuring a particle state is akin to determining the coffee's temperature, but before the measurement, the temperature is a mixture of all possible states. ORSF suggests that if two friends measure the temperature from different angles, their readings will be consistent, reflecting the coordinated system that ensures coherence. Addressing potential contradictions with special relativity, particularly in the context of space-like separated measurements, poses another challenge. Classical concerns focus on maintaining consistency without violating relativistic principles. The ORSF approach offers a solution by proposing a special time order or a frame-dependent reality, ensuring that consistency is preserved without observable contradictions. Conclusion: Qian Li's paper advocates for a paradigm shift in quantum mechanics interpretation, offering a coherent framework to address long-standing paradoxes such as Wigner's friend scenario. By redefining Born's rule and introducing the ORSF, the paper lays a robust theoretical foundation for comprehending quantum measurements and entanglement. Synthesizing these concepts, Qian Li's work presents a transformative perspective on quantum mechanics, emphasizing the coherence of entangled systems and offering a new pathway to understanding quantum reality. This comprehensive analysis invites further investigation and debate within the scientific community, highlighting the evolving nature of quantum theory. Thank you for listening and stay well.